Welcome to the concept of control chart. Concept before going into the concept of control chart, we have to understand one single thing: why control chart was introduced earlier. Control chart was introduced to form a particular solution to a term called statistical, or is a part of solution to the process control. Process control means even if an organization is getting good result with a certain kind of process associated with it, it can get better. And while talking about betterment, we have to compare the previous kind of data that we are getting with the process and the newer kind of data that we are wanting to get. Now this expectation level with the current one, if we are comparing it, we can definitely better the kind of control on that process by implementing this particular concept of control chart. This is control chart is a basic tool used for should I say displaying the inspection results of a sample of a particular product. It can show you it can show you students the derived statisticals limit, which helps to discriminate between a random variability and an assignable variability. Every single control chart is consisting of three lines: a central line, an upper control limit, and a lower control limit. Any kind of control charts can be generally divided into two types. One is called control charts by variables. Another one are control charts by attributes. Control charts by variables can be treated as X bar R chart, and the attributes charts are known as the P chart, C chart, and NP chart. If we talk about initially the first chart called the X bar chart. X chart or the X bar chart is basically the average chart that we generally talk about. Average chart generally talks about or measures the central tendency of any process. The range chart or R chart talks about the spread of that process or measures the spread of the process. These two charts, X chart and R chart, are used together and commonly known as X bar R chart. As I was talking about the P chart is generally known as the fraction defective chart, which records the proportion of defective items in a sample. NP chart is also called the number defective chart, which records the number of defective items in a sample. The defects chart or the C chart records the number of defects in a component or a particular product. These are the different kind of control charts that any organization generally use while talking about control charts. As we were talking about, X bar R chart is a pair of chart consisting of an average chart, which is called the X bar chart, and a range chart called the R chart. The basic theory behind this X bar R chart are based on the concept that the average of a sample of several items tend to cancel out the normal process variability and the undesirable changes due to assignable causes, thereafter, which becomes very visible. Most importantly, we can definitely say that the upper and lower control statistical limits are worked out and inserted into this particular chart, as we were talking about the should I say the upper control limit and the lower control limit. In this particular chart, the central line is given as the X double bar, or the mean of the mean. That is what we mean by it. And most importantly, the upper control limit is given as X double bar plus A2 R bar. Again, R bar is the mean of the total range, and A2 is a particular should I say constant which will be given and is not within our limit to calculate that particular thing. And lower control limit of x bar chart is x double bar minus a2 r bar. And most importantly, for r bar, the central line is r bar, and most importantly, the upper control limit for R chart is D3 into R bar, and lower control, I'm really sorry, D4 into R bar is the upper control limit of R chart, and lower control limit of the R chart is D3 into R bar. For your, should I say, betterment, I have listed down all the formulas, and you can find it out in the last slide of this particular PPT or this particular video. You will find out all the formulas have been jotted down in a particular page so that you can be benefiting from that one. So moving on, as we were talking about XR chart, let's talk about an example of XR chart. As you can see, it is a very detailed one. How do we understand this particular example? That one single sample has 5 different results. So sample 1 to sample 10 each has 5 different results attached to it. Like for sample 1, I'm just mentioning here, sample 1, 25 is the first result, 25.01 is the second result, again 25 is the third result, 25.03 is the fourth result, and the fifth result is again 25.01. So similarly, it continues from 2 to 10. So what we need to do, we need to plot the X bar and the R chart and find out which of the given observations are out of control. As I was telling to you guys that A2, D3 and D4 are all constants and will be given to us. So you can see here the value of A2 has been given at 0.5768, D3 has been calculated at 0 and D4 is 2.114. To move on with the calculation, we first need to find out the X bar chart. While talking about X bar chart, for sample number 1, if we take the mean of X to be X bar 1, so now as I said, each sample has 5 different results. So the first sample is having the result of 25, 25.01, 25, 25.03 and 25.01. So how to find out the mean? For sample number 1, we will add up all the sample value that has been given to us for sample 1 divided by the number of repetitions. Here the number of repetition is 5. So adding up all the values, we are getting 125.05 and dividing it with the number of repetition, we are getting the mean of sample 1 at 25.01. If this is the mean that we are getting for sample number 1, simultaneously now students, you have to just find out the arithmetic mean for all the samples from 2 to 10. And you can see here, I have found out all the arithmetic mean of the samples and just cross check the values whether it is matching with me or not. Coming back, to find out how to find out the range for one sample, I'm just showing you for one and then you can do it on your own. Just find out, just see here that the maximum data available for sample number 1 is at the 4th repetition, which is 25.03, and the minimum data available for us is at repetition number 1 and repetition number 3, which is at 25. So highest minus lowest, again I am repeating, the highest minus lowest of any sample, that should be highest minus lowest should be the range for each sample. So for sample 1, the highest minus lowest is giving me the value of 0.03. Simultaneously, if we can calculate it back to sample 10, we are getting the values according which I have shown it in the slide itself. So these are the values. So now we are clear how to understand the arithmetic mean of each sample and how to find out the range of each sample. Moving on with the solution here, now we need to find out the grand average. What is the grand average? The mean of all the means. As I was saying, the formula for x double bar is the arithmetic mean of all the samples divided by the sample number now. So as we have found out in the previous slide, we have found out the arithmetic mean of all the samples. So simultaneously I'll just put up all the values here and add it back, and then I'll divide that particular value of 250.10 by this number of samples that we are having here, that is 10. So the grand average or x double bar is coming at 25.01, whereas the mean range or the R bar is somewhere coming at all the ranges that we have found out in the previous slide. That is by calculating the highest minus lowest range. The subtotal is somewhere coming at 0.40 divided by the sample number. We are finding out the range or the R bar to be 0.04. Now moving on to the calculation part here. As I was saying, we have three kind of lines here: central line, the upper control limit, and the lower control limit. So the central line here, we are talking about the x double bar. X double bar is actually already calculated at 25.01. The upper control limit is calculated at x double bar plus a2 R bar, which we can the value of a2 has already been given to us at 0.5768. You can find it out in the sum itself, and multiplying it with the R bar, we are getting the value at 25.03. And the lower control limit we are finding out to be at x double bar minus a2 R bar, and if we can calculate the value back, we are finding out it at 24.99. Now coming back to the most important part of any control chart sum, we have to show it graphically what we are trying to mean. If we are seeing now, in this particular graph, I have taken the sample of 10, which has already been given to us, and I have plotted the mean value of each sample in this particular graph, taking the upper control limit to be 25.03, the central line to be 25.01, and the lower control level value to be at 24.99. So now if we find out that if we plot all the values, we find out that the 10th sample, which is having the value of 24.98, that particular value is not coming under the control, is not coming within the prescribed control lines here. So that particular sample is out of control. If, remember this class, even if one single sample is out of control, it makes the entire process out of control here. As we have found out that, continuing with the sum, that we have found out that 10th sample was out of control here. Now when we talk about how to rectify that, so now what we do, we leave out that particular sample. Once we leave out that particular sample, the sample number moves back to 9. When we move back to the sample number 9 now and calculate the rest of the x double bar and R bar, we find out that x double bar is somewhere coming at 25.01 and the R bar is coming at somewhere 0.039. The process is absolutely same like the previous one, just here the sample number has changed from 10 to 9. Moving on with the calculation of central line, lower control limit and upper control limit, we can easily find out that the central line is coming somewhere at 25.01, the upper control level is coming at 25.04 and the lower control limit is coming at 24.99. So when these three lines has been obtained by us, now if we put back the same kind of values with the upper control level, lower control level and the central line, now we can plot and see that each single line, each single point is coming within that prescribed guideline, within that prescribed line of the upper control limit and the lower control limit. So now we can definitely say, yes, this X bar chart is within control. So this is how we draw the X bar chart. And not only X bar chart, remember class, we have to draw each and every single chart that we are calculating. Moving on to the R chart calculation, the central line for R chart is given at R bar, which we have already calculated new at 0.039, or we can transfer the value at 0.04. The lower control level, as we have said, it to be D3 into R bar. As D3 has been given at 0, the entire value moves back to 0. And the upper control limit has moved back can be calculated at D4 into R bar, where D4 is a constant, as I have previously mentioned. D4 has the value of 2.115, where the R bar value has already been calculated at 0.039 rather. So the value generally transfer back into 0.08. Now, I have not shown it here. This is your responsibility how to draw an R chart. Here you have the central line, you have calculated the lower control limit, you have calculated the upper control limit. Just draw the line with 9 different results, and those 9 results which you will be putting in the R chart will be the range that you have found out previously for the each sample. That's what you will be putting in the R chart graph. Kindly do it and check whether the process is under control or not. Until that particular part has been completed, the sum is not completed. Let me remind you once again. Let's move back to the concept of fraction defective chart or the P chart. The control chart for fraction defective is used where the products manufactured in the organization are inspected and can be classified either accepted or rejected. This particular part can be furthermore, this rejected particular part can be furthermore divided into spoilage or a certain kind of rework. So if we talk about what do we mean by fraction defective chart, this is a certain kind of thing which records the number of items rejected to the number of pieces inspected, calling it, thus the name here it comes, the fraction defective. So this is how we generally find out the fraction defective chart. Let's go into the furthermore example of fraction defective. I'll not elaborate on the theory how the standard deviation is found out or something of that sort. We'll just go back before going into the example. Just I'll remind you of the formulas that are associated with should I say the fraction defective chart. Is that the central line is generally the P bar. Central line is generally the P bar. I'll come back how to calculate it. The upper control limit is the formula is practically P bar plus 3 into root over P bar into 1 minus P bar divided by n, and the lower control level is P bar minus 3 into root over P bar into 1 minus P bar divided by n. As I have previously mentioned also, for your betterment, I have just recorded down all the formulas and put it into the last slide of this particular video. So kindly go back and check out what are the formulas that we have been talking about. So taking an example now of the fraction defective chart here, 10 samples of each size 50 has been inspected by an organization. The results of the inspection are generally given below. So we can find out the sample number that are there 1 to 10 and the number of defects that are there. We need to draw a P chart and we have to state our conclusion. Coming back to the solution of a P chart here, as we were talking about, we have the sample numbers which have been given and the number of defectives we have been talking about the number of defects that are there in each sample. We can find out that and add back the total number of defects to 20. Now coming back to why this particular method is talked about as fraction defective. In the sum itself, we have seen that each sample has a sample size of 50. So one sample is equals to 50 units. Now, how to find out the fraction defective? The defect that are there in one sample divided by the number or the size of that sample. So I am giving you one example. Suppose if I talk about sample number 1. So sample number 1, or here it is constant. So sample number 1 to sample number 10. Each sample number will have the same kind of size, that is of 50. So now if we talk about the number of defects here, sample number 1 will have the fraction defect of 2 by 50. Very similarly, the sample number 2 will have the defect of 3 by 50, and continuously it will go on. So 2 by 50 or 3 by 50 should give you the fraction defective value, which we are getting it at 0.04 or 0.06. Now if we add back all the fraction defects here, we get the total fraction defective to be at 0.40. Now if we talk about the average fraction defective, that is P bar here, we generally do what? The total fraction defective divided by the sample number, which is at 10, which gives me the P bar value at 0.04. If you do not like to solve the particular P bar this way, the alternative method is that the total number of item that we are inspecting is sample number of 10 and each has a sample size of 50. So the total number of items that I am inspecting is 500. The total number of defects that are there, which we have already counted at 20. So the average fraction defect should be the total number of defect divided by the total number of items inspected. So that is also 20 by 50, which is again giving me the same kind of result at 0.04. You guys are free enough to go with any kind of method, any of the two methods that you are wishing to. Now the central line, as we talked about for P chart, was P bar, which is already calculated at 0.04. The upper control limit and the lower control limit formula that I was literally telling you just the previous slide. We can see here the upper control limit formula is P bar plus 3 root over P bar into 1 minus P bar divided by N. Now here comes one more thing here, that this particular small n is the sample size that we are considering. We are not considering the total number of items that has been inspected. That is the sample size here and not total number of items. Please be clear with it. If we are clear with it, the upper control limit should be calculated at 0.123. One more important term here. Here you can see the lower control limit has been calculated to negative 0.43 here, or 0.043 here. Class, just remember one thing, or students just remember one thing, that no limit is there beyond 0. You cannot draw a graph, or any error cannot be calculated or cannot be shown in a graphical method at negative. And since any error or any tangible error cannot be beyond 0, so whatever, for any kind of, this is not only for P chart, this is applicable for all the charts here. If any upper control, lower control value comes beyond 0, if it is coming at negative, we will transfer that value back to 0 itself. Again, I am repeating here because this is one of the most important part, that if any upper control level value or the lower control level value goes back and comes at negative, since no error or any tangible error cannot be calculated beyond 0, cannot be calculated at negative, so simultaneously that value we will be transferring back at 0. So here you have the upper control limit and the lower control limit. Very similarly, this is again your homework, or you might do it on your own. Draw a certain graph and show whether the values are under control or not. Then only the sum should be completed. Generally, if you want the answer here, yes, according to my calculation, the P chart is generally coming under control. Now check the sum here, whether you guys can do it or not. Moving on from the P chart to the concept of NP chart. There's a bit of difference between the P chart and the NP chart, as P chart, unlike or NP chart, unlike P chart, records the number of defects instead of the fraction or the proportion of defect. So here the total number of defect might be calculated in this particular NP chart. You can easily say that in NP chart the P bar is very similar, or is very similar to the calculation of the P bar chart, right? So if we go now with an example, if we take the same example than that of should I say the P chart here, we can see the second part or of the calculation of P chart, which I have shown in the formula in the previous sum here. The sum of defective samples divided by the total number of pieces inspected. If we go back now, we can easily find out that to be 20 by 500. You can go back to the previous slide and check it. That is coming at 0.04. Now the central line of the NP chart is calculated at n into P bar. So again, as we have said, and I have explained it in the previous slide itself, that n is 50 here and not 500. So 50 into 0.04 should give you the value of 2. And upper control limit and the lower control limit formulas are subsequently n into P bar plus 3 root over n into P bar into 1 minus P bar, and just for lower control limit that will be negative. Just that. So calculating the upper control level and the lower control level, we are finding out the upper control level value at 6.17 and the lower control level value we are finding at negative, which we are transferring back into 0 again. We have the central line, we have the upper control limit, and we have the lower control limit. So you can again draw the graph, and for your hint, that the points that are there are absolutely within this particular limit. Just go on and check it whether you are getting it or not. Moving on to the concept of control charts last variant, that is the defects chart or the C chart we call it. This is a particular chart where we measure the number of defects in a particular product, as we have talked about in the earlier thing. A control chart which exhibits the counted data on the number of defects is practically called a C chart, as we have talked about. The quality characteristics in this chart therefore is the number of defects per unit. So this is a whole number of defect which we are calculating. A product may have more than one defect, but all defects are not of equal importance while calculating the C chart. So if we now go back, the central line formula for C chart is C bar. The upper control limit formula for the C chart is C bar plus 3 into root over C bar. And the lower control limit formula is C bar minus 3 root over C bar. Moving on with the sum here, as we have done for most of the control charts. What has been given? A certain number of defects has been found out in the sample number from 1 to 10. So we need to construct the control chart for the total number of defects here. So moving on with the calculation, as I have just said, the central line calculation for C chart is the C bar which is the total number of defects divided by the total number of samples. Now if we put on should I say the value here, if we add back the should I say the number of defects value, we will definitely find it at 30, and the sample number is given at 10. So definitely 30 by 10 should be 3 here, and the upper control limit value, if we put on all the values here, we can get it up to 8.2, and the lower control level formula, as we have talked about, c bar minus 3 into root over c bar, we are getting the value at negative 2.2, and we can transfer it back to 0. Now if we plot back using the control chart here, if we plot back, you can see here I have plotted it back, and all the values are within control. So if all the values are in control, we can definitely say that this particular process is definitely under control.